Okay, hello everyone, and welcome to the 11th seminar of our series celebrating INGV's 25th anniversary. It's my great pleasure to introduce Emeritus Professor Yosihiko Ogata, I hope the pronunciation is correct, who will present today's seminar entitled Development of ETAS Models before its birth to today. Before giving the floor to Professor Ogata, a few words about his biography. He is a leading expert in statistical seismology with over 40 years of experience in the field. Professor Ogata is Emeritus Professor at the Institute of Statistical Mathematics, ISM, in Tokyo, member of the Statistical Seismology Research Group at ISM, and Emeritus Professor at the Graduate University for Advanced Studies, Sokendai, in Japan. He was a pioneer in modeling the earthquake process as a stochastic epidemic branching process, introducing the epidemic type aftershock sequence ETAS model, whose lifetime and developments he will present today. ETAS is, to date, the most widely used model in probabilistic earthquake forecasting applications worldwide. As a member of the leading research group on statistical seismology established in Japan in the 70s at ISM, he collaborated with prominent personalities in this field, including the late Professor David Verre-Jones, whom we remember with great respect and deep emotion, as he recently passed away on October 31st, 2024. During his remarkable career, Professor Ogata has made significant contributions to the theory and application of statistical seismology, author of several foundational most cited works in the field. He is a member of notable scientific associations like the American Geophysical Union and the International Statistical Institute, where he was elected. He also won several prestigious prizes, among which the Japan and Korean Statistical Society Prize, the Seismological Society of Japan Prize, and the top 50 citation of Tectonophysics 2005-2010. He is also a member of many international scientific committees and advisory boards, like for several workshops on statistical seismology, StatSei conference. I furthermore would like to remember his postgraduate supervision and external examination of several scientists of note like Jiankan Zhuang and David Harte. His main lines of research include forecasting the magnitude of the largest expected earthquake, developing more sophisticated ETAS models and their applications to regional and global seismicity, prediction and validation of short, medium and long-term earthquake probabilities, aftershock forecasting based on incomplete earthquake catalogs and foreshock characteristics versus forecasting in synthetic and real earthquake catalogs, cluster analysis of spatial point patterns. We are deeply grateful to Professor Ogata for accepting our invitation, and we now look forward to his presentation. For questions, please fill out the form available on the INGV Eventi YouTube channel. Thank you very much. Professor, the floor is yours.
Okay. Thank you very much. Very nice introduction for me, and I'm very glad to talk about our work. First of all, sorry, I would like to pay special thanks to Professor David Verre-Jones. He passed away at the end of last month. David invited me to join statistical seismology 50 years ago and always encouraged me. Here are contents of my review paper that has just published in Annals of Geophysics for the 25th INCV anniversary issue. I have prepared many slides for this presentation, and I am afraid that there is not enough explanation on each one. So if you are interested in, please refer to the paper. The section 2.2 contains some important statistical seismology studies in Japan. This shows the number of earthquakes felt each month at the nearest station after Novi earthquake. Omori says that the decay in the number of aftershocks is not exponential, unlike the decay in many natural phenomena. But this fits well into a hyperbolic function. So this is a start of kind of a statistical seismology for me. Incidentally, here is my personal output. Anegawa earthquake occurred in 10 years after the Novi earthquake. Before the Anegawa earthquake, the number of aftershock has been lower than the predicted decay for about 8 years. In a later section, I will discuss this phenomena in detail. Here is the original and heuristic method of Utsu. At that time, he used the double logarithmic graph papers and found that the fitted asymptotic straight line has continued for more than a century. The C-curve is considered for initial curvature. So Utsu made many such graphs and found that p-value for the slope is not always 1 in many cases. He also found that the secondary aftershocks still follow Omori-Utsu decay formula. These graphs were made by counting the number of aftershocks in suitable time bins. After 1983, thanks to the point process, the maximum likelihood method are used directly based on the occurrence records. Now, I'm going to introduce epidemic type aftershock sequence model, or ETAS model for short. Then I'd like to explain how to use the ETAS models. The ETAS model predicts the occurrence rate of earthquakes in a region by a history of times and magnitudes. This rate is superimposed by the weighted Omori-Utsu functions and constant parameter mu. According to the Utseki law for the aftershock area, the weighting is an exponential of magnitude adjusted by a factor alpha. The cumulative record curve, red curve, for the ETAS model match the black curve for the actual aftershocks. The second panel shows the magnitude versus time. The third panel shows the ETAS intensity rate. This shows the similar for the long-term data in the Western Japan since 1926. The integral of the Omori-Woods rate transform the occurrence times for the trending. This curve transforms the aftershock times to obtain the uniform distribution. The detrended times often appear heterogeneous space-time pattern, but in some cases uniform. The former cases are interesting to find some seismicity anomalies, and I will show you more cases later. Any model, including the ETAS model, can be transformed in the same way for the trending. For example, here is the aftershock records of large earthquake in this region. First, we apply Omori-Woods formula to the aftershock until 1,000 days. It doesn't seem a straight line. And the bump here is because of the largest aftershock that triggered many aftershocks. If we apply secondary aftershock model, we get linear cumulative function up to 2,200 days, but then it slopes upward. If we apply the ETAS model for 3 months, we get a plot like this, which then becomes linear till another 15 years. Next, I show you some applications of non-stationary ETAS model. This defines a non-stationary ETAS model. The cumulative red curve mu t and the black curve kt are calculated using piecewise linear functions. We have found here that many peaks in the mu t curves match with non-slow slip. These slips were reported by the inversion from tiltmeter records or GNSS locations. Earthquake swarms in region B are also associated with slow slip. In particular, the Tohoku-oki M9 earthquake induced slow slip. These are activities in this volcanic region along Japan Alps, and the peaks of the red mu curves are associated with rising magma. This is long-term series of earthquake swarms off the east coast of the Izu Peninsula. Here the red curves are mu-T curves, and the green arrows indicate the 8 active periods. These are selected and expanded as given here. The black curves here show the background rate mu-T. Then we have predicted the background rate as shown by the red curve. These are calculated for the red color mu tilde function from strain change data. These agree with the non-stationary ETAS mu values for all the swarm activities. This particular aftershock activity appears to include different triggering mechanisms because mu-T are not constant. The time span during this pink shade around the mu-T peak correspond to the cluster of red epicenters in the left bottom panel. We believe that this is due to the water intrusion into this area. In contrast, little changes in mu-T was observed for the largest aftershock in 4 months later. Next, let me show various space-time ETAS models. On the space-time extension of ETAS model, we compared 3 candidates for the spatial response functions. They may have elliptic contours for some large earthquakes, but for simplicity, we show here the isotropic case. The first case is a short-range scaling in distance. The second case is inverse power decay. The third case is asymptotically inverse power decay with near-field scaling. According to the Kaike information criterion, the third case is the best fit for these areas in Japan. In addition, I extended the spacetime model to include location-dependent parameters. As the data increases or the region becomes larger, the model parameter takes different values from location to location. Therefore, we need to make each parameter a function of location. I call this the hierarchical space-time ETAS model or HIST ETAS model. These parameters in piecewise linear function on the Delaunay tessellation made of earthquake locations. To avoid bumpy fluctuations of parameters due to overfitting, we need suitable penalties. Here are optimal parameter estimation in Japan. These are estimates of mu, k, alpha, p, and q values at each earthquake location. The mu and k values are interpolated to produce images like the one shown here. So these are interpolation, linear interpolation. These are also of alpha and p-value images. The detailed image can be seen in the region of many earthquakes. This is the advantage of Delaunay tessellation-based parameterization. In addition, here is a Delaunay tessellation from the global CMT catalog, and this image shows a mu image of this subregion. Similarly, here is a Delaunay tessellation from the JMA data. This is mu image mainly on the Pacific plate. I have constructed the Delaunay tetrahedra under the Tokyo area and constructed the three-dimensional HIST ETAS model. These four panels are the mu image as of June 2018, predicted on the sectional surfaces, which are the 10 kilometer, 20 kilometer depth horizontal planes, the upper surface of the Pacific plate, and the Philippine Sea plate. The plus signs indicate the earthquake of magnitude greater than M3 that occurred near each surface during the next 6 months. In addition, these earthquake magnitude greater than M4 occurred within the next 2 years. So the prediction seems to be working quite well. Now recently, I have been doing a forecast and assessment in Japan. Instead of using active fault data, I have recently proposed a long-term forecasting method using the background seismic activity mu values of the HIST ETAS model. Unlike the Poisson plots on the top panels, the mu estimate is stable over the learning periods, independent of triggering effect of the M9 Tohoku earthquake. I have compared the mu estimate with other models. This is the best at predicting the location of large earthquakes of magnitude M6 or greater, M6 or greater over the 30-year period. It also has the best agreement with the location of historical damaging earthquake. Let's take a look at the short-term space-time predictions and their evaluation. This is a short-term forecast. This is visualized with the moving images. Once again, I evaluate the forecast using log likelihood or information gain. The best overall forecast is detailed ETAS, which reflects the regional characteristics. The difference in scores indicate the relative merit of each earthquake location. First, as indicated by the red triangles, results are poor for volcanic storm activity. Performance is also poor in areas with low mu values, which means we haven't had enough data in the past. Let's see some progress in aftershock forecasting. In fact, predicting aftershocks in real time is difficult. This JMA report shows that the total number of aftershocks varies by a factor of many times, even for main shocks of similar magnitude. Moreover, the majority of large earthquakes occur within a day, 1 day, but the missing aftershocks in the period are huge. So detection date of aftershocks immediately after the main shock is modeled in this way. The parameter mu is the magnitude at which half of the earthquake can be detected, and sigma is the detection width. This is multiplied by GRO, Gutenberg-Richter's law. The logarithmic scale of the vertical axis gives the shape of these frequencies. Here the change in mu value over time makes a prediction. The maximum likelihood estimate of the 6 parameters predict temporal changes in magnitude frequency well. The blue solid curve is the MLE used earlier, and the red solid curve was obtained using the Bayesian smoothing method. The predictions are almost identical except for minor details. For the past 5 years, we have been making real-time forecast from the HiNet automatic records. Among the 40 cases experienced, the Kumamoto earthquake has a much larger k-value than the others. The 4 color curves here show the probability of an aftershock exceeding magnitude MT within 1 day, where the MT is a horizontal axis. In case of the first Kumamoto earthquake, the probability of aftershock larger than the main shock occurring within 1 day ranged from 30% to 10%. In other cases, probability was less than 10%, often a few percent. For unbiased medium-term forecast, the Omori-Woods formula in the Riesenberg-Jones model is replaced by the estimated ETAS model within 1 day. Now let's estimate the ETAS models from very incomplete data. Very incomplete data in case where all detection parameters changes. The parameter mu, b, and sigma values are presented by cubic spline functions of time, and these solutions are obtained by maximum penalized log likelihood. In addition, it is necessary to adjust the 6 weights for the smoothing. To do this, we adopted the Bayesian inference with 6 hyperparameters by minimizing the Akaike Bayesian information criterion. To estimate the underlying true ETAS model, we define the intensity C rate applied to the incomplete data. Then we can define the log likelihood. For a stationary ETAS model, we obtain the MLE. For a non-stationary ETAS model, time variations of the mu and k values are penalized for smoothing. The 2 weights are adjusted by the ABIC for the optimal smoothing. We see that the parameter changes in both B and sigma are very different in the two Noto Peninsula aftershock sequences. For example, the difference in the sigma value is due to the different sizes of the aftershock area relative to the station configurations. The blue curves here are the changes in the detection rate of aftershocks above a certain threshold magnitude. The underlying stationary ETAS model is best choice for the 7.6 aftershocks, while the non-stationary ETAS model is chosen for the latter aftershocks. The main difference is the changes in the mu values, which are interpreted as whether or not significant dynamic stress is present or not. Here we take a look at retrospective anomaly that may be applied to forecasting. The red curves, cumulative curve shows the ETAS fit to the aftershock 1 week after the Chuetsu earthquake. About 6 months later, we had less aftershocks than the expected for about 2 years. Then, the Chuetsu Oki earthquake occurred nearby. The earlier earthquakes in the Chuetsu Oki source region have migrated to deeper locations, and the decrease in distance of DNSS baseline along the coast has slowed, which confirmed the slow slip. And we believe that this slow slip made the stress shadow in the aftershock region of the former 2004 Chuetsu earthquakes, which caused the relative quiescence. Also, here is another precursory scenario before the 2004 6.8 Chuetsu earthquake, which assumed that there was a slow slip in the deeper part of the Chuetsu earthquake fault. I skipped this, and please see my and our papers for details on this and the other anomaly scenarios in Japan and California in the reference of my paper. This is the last section that includes my issues for many of you to aim at the practical forecasting for the future. The predicted probability of a large earthquake from a single anomaly prediction alone is very small. But when the probability gains of several independent anomalies are available, in addition to the background probability of the large earthquake, multi-element prediction equations can be significantly improve the overall probability prediction. I have retrospectively calculated the multi-element probability forecast for the 2016 Kumamoto earthquake or independent anomalies, I used active fault rupture forecast and foreshock discrimination. And for the medium-term forecast, I used relative quiescence from the ETAS model. The multi-element probability forecasts were then calculated for combinations of independent cases. The relative quiescence predict when the major event is likely to occur and where it's likely to occur. To assess this, we use the ETAS to examine the aftershocks of 76 major earthquakes that have occurred since 1 century ago. Relative quiescence have been observed in about 45% of the aftershock quiescences. In this case, a histogram with a large probability gain is obtained within 6 years. This is several times greater than the space-time ETAS trigger gain. This probability gain is incorporated into was incorporated into the multi-term forecast. Another one, there is a review paper suggesting that slow slip could lead to a similar gains of earthquakes. This shows superimposed relationships from a slow slip to nearby large earthquakes. Now, please remember the previous slides about the non-stationary ETAS model. In many cases, the swarm earthquakes are synchronized with slow slips. In order to increase the number of slow slip cases, we can study the peaks of mu values of the swarm activity.
Professor, you
Next.
have 5 minutes. Sorry.
How much?
5 minutes.
Okay.
Thanks.
Yes, that's enough. There is also a study that tried to detect causality using a Morchan plot. They examined the maximum variation with moving time windows of the trended time series of the GNSS baseline distance. Probability gain is about 2 against the independent occurrence of earthquakes of the East Coast. As we saw earlier, this space-time diagram that has been time converted using Omoriut's method. In addition to cases where the events are almost uniform over time, as shown in the top panels, there are many non-uniform trends, and it appears that large aftershock seems to somehow related to the heterogeneous occurrence patterns. I have discussed such patterns causality based on the Dietrich latent state friction model, but the challenge is how to quantify anomalies from the forecasting perspective. Well, this is the last slide. Each section contains some unsolved problems at key points. If you are interested, please accept the challenge. Thank you very much. That's all.
Thank you very much, Ogata-san. And it has been a real pleasure. Thank you. It has been a real pleasure, because I think that you inspired generations of statistical seismologists. For sure, your works inspired me a lot about what I've done in these years. So, if you have specific questions, just please approach to the podium. Oh, yes, please, Rodolfo.
Can you hear me?
Yes.
Okay. Thanks a lot, Professor Ogata, for your presentation. It is impressive, the quantity of information that is contained in the presentation. Is it in the article in the Annals Geophysics? Okay, yeah. Very important. Could be used as a reference for courses, university courses, for instance, for PhD studies and so on. Very, very good. Let me recall 26 years ago, in 1998, just the year when the space variable ETAS model was published by Professor Ogata. I was working in Tokyo during this period of the year, this time of the year, near winter, before Christmas. And I had developed independently of Professor Ogata a similar model in my stage for 3 months in Earthquake Research Institute, Tokyo University. And I went to Professor Ogata's office to discuss with him my work, but he gave me his publication. It was just very fresh. It was published that year, including what I had done already. So it was impressive. And I also followed the work of Professor Ogata in the following 26 years, and you have seen how much he worked. I have a little question, or a point that was rising in my mind during the presentation, that most of the equations here, the models, are assuming a constant b-value. Professor Ogata mentioned the Gusemer-Ritter equation, and also for them, the b-value was constant. So the magnitude distribution is not changing in time. But there are recent observations showing that in some cases, before strong earthquakes, the b-value is changing. And there are publications about it. My question for Professor Ogata is, what do you think about this kind of possible precursors, besides the ETAS model, to be used together with the ETAS model? Thanks.
Well, I know there are so many papers about B values. But prediction for B value discussion based on the for the prediction will be quite complicated for me, because the B value, some experiment of rock sliding, there we can observe some stress changes, but the B value actually is very much sensitive to the locations. Because of the geology is very complicated. So we should be very careful about the discrimination between the time change of B value and the space location. The most difficult one is that migration of earthquakes. If earthquake migrate, then it means that the location is changing. That means the B value can change, able to change. So I try to make something uh, to make a forecast based on the B value. It's published in not a BS SRL paper, but it doesn't work very much because I don't know. Actually, my variation it wasn't very good.
Mm.
So p-value studies have very so many works, but need to me to persuade the very clear discrimination of p-value changes. That I'm sorry, I cannot say more than that in this short time, but I need even I showed the even aftershock sequence changes, p-value changes. So that is the difficulty, very, very difficult. But needs, one thing is we need to make a evaluation system to check. Maybe it's based on the scores or something like that, giving many focus based on the B value, if one believes that is quite useful.
Okay,
Thank you very much.
Thank you very much. It was very clear. Massimo Cocco, please approach the podium.
Ogata-san, it is a pleasure to see you even remotely. I still have a nice remember memories when the time spent with
Yes,
you.
I remember.
Yeah, and the time
you are with David Bear Jones.
exactly.
For our reviewing our project.
Exactly.
Thank you very much in that case.
Yeah, exactly. No, but with David and Bill Ellsworth. So it is really a pleasure to see you. And I have two questions. One question concern again is just following Rodolfo's question, which concern the B value, because the B value might change in space, and we see large variation in space of B value, in particular in geothermal applications. When we apply the ETAS model to induce seismicity, we have a lot of problems in making any type of forecasting, essentially because of no stationary, of the difficulties to estimate the background, of no stationarity of the sequence, but mainly because B value is strongly changing in space. So what is your perspective of using ETAS and also the time prediction for this type of induced seismicity?
Well, actually, the B value itself is just the inverse of moving average of magnitude. So it have a very simple statistics, and recently I'm going to look at the aftershock itself, because aftershocks are quite occurs in a very narrow region. So maybe location doesn't may play very much. So if I talked about the day trending using Omori-Utsu formula, determining not the determining of ETAS, the trending with the omori with the formula and look at this by the space-time pattern. So B value may changes, spatially, how the spatially changes. If you look at for example, if you are interested in the large aftershock forecast, how the relationship between some patterns and the large aftershock frequencies of. What I'm saying is just a probabilistic research. So not that not the deterministic ones. So need some kind of evaluations and modeling is only the way for the using p-values. Is that okay?
Yeah, yeah. And actually, this is also something that with Stefan Wimmer we are trying to do to the stimulation in underground laboratories. So yeah, that is more or less the direction. So the second question concerns the slow sleep. So in general, any type of aseismic deformation or let's say deformation that are different from aftershocks or seismicity should present let's say a perturbation, no, to the forecasting, a complexity in the forecasting. Now the question to you is the following. You extensively presented the slow sleep, but where the slow sleep should affect ETAS, in the background or in complexity in the homology decay? So is this in the clustered part of the prediction or in the background function?
Could you say it again, please?
Yeah, my question concerns the slow sleep and the complexity that the occurrence of slow sleep events can create to the ETAS forecasting. And my question is where these slow sleep events affect the ETAS predictions, in the background contribution or in the clustering part?
I cannot say answer about that. This is just I'm starting to look at carefully about the background rate pattern, but other ETAS parameter may not I haven't studied yet.
No.
Maybe K value change is much sensitive compared to other parameters like P value.
Thank you, Ogata-san, and I hope to have a chance to meet you soon in person in the future. Ciao.
Thank you.
Okay, thank you. Other questions? No, I have, of course, I have some, and okay, the first one is about the hierarchical ETAS model that introduced the spatial variability of some parameters. I'm just interested in understanding what is your perception about the advantage of this model with respect to more classical ETAS model. Let me make an example. I think that trying to model with classical ETAS model the Japanese seismicity, we see that there was a significant difference between the seismicity offshore and inland. So I'm interested in understanding if the advantage of the hierarchical ETAS model is mostly due to this kind of different seismicity offshore or inland, or the difference is also due to some other kind of feature of the seismicity, at least in Japan.
I just started the inland one, because the government want to establish the forecasting, long-term forecasting. But of course, the offshore one is quite more active, and I I'm going to do that. But the here is at least here is a comparison with the classic 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 one is not here. Sorry, classic one isn't given here, but it's not the best. Classic one for is just for the places where the for example, this is not all is was not well predicted.
Okay.
And other places like here and some place like here. Before Tohoku earthquake, it wasn't not active. It not active very much. So in that sense, history ETAS model is much more complicated
So,
for location. So if data is not enough, with the classic ETAS model, space-time ETAS model works better.
okay. So let me, if I understood correctly, you find a clear advantage also inland for using hierarchical models inland with respect to the classical ETAS model. And I'm interested in understanding a little bit more something about probability gain, for instance, for large earthquakes. Because if I understood correctly, but please stop me if I misunderstood, you compare this model using some sort of archaic information criterion. And that's okay, of course, but my question is just in terms of forecast, what is the difference in terms of probability gain for the hierarchical model and the classical model? I'm trying to understand what is the practical advantage.
Okay. Probability gains, I just first start from the study of what you call score, information gain first.
Okay.
Then as given like here, can you see the this shown, we can compare the probability gain, comparing this, we can calculate the probability of inland from both history ETAS model and just a space-time ETAS model, and compare the ratio. It depends on the locations. The probability gain depends on the locations.
Okay.
So,
and
so that it's, oh, why? You know, the Bayesian model is sometimes shows a very detailed, but from the predictive viewpoint, we need this likelihood. So I don't use ABIC nor AIC because we already have estimated the parameters for the future data.
okay.
So these are evaluated by the future data, which means like after 21st century studies.
Okay.
So there's a learning period we can use AIC or IBIC, but this prediction may just we can use
Okay.
log
The
likelihood
log
or information gain.
Yeah. Okay. Thank you. And I think that there is time for another question. Yeah. And I would like to understand something about the role of uncertainty. I know that you co-authored some paper with Omi-san that try to investigate what is the role of uncertainty in forecasting. And I'm just, yeah, what is your perception about this? Is it important? If so, where exactly is important to account for uncertainty in forecast?
Uncertainty
On the parameters.
forecast.
Yeah.
Where did I cannot see where the maybe this.
Even just your perception, your feeling, because yeah, I see that.
Well,
Yeah.
uncertainty is from the in the Bayesian case from the posterior distribution.
Yeah.
The Omi-san and our paper can make uncertainty using simulation, using posterior function. He used state space modeling and easy to simulate it, so that this provides uncertainty. But in other cases, when I use other method, maximum likelihood estimates gives the uncertainty as well. But for the another much more complicated one is just using maximum a posteriori estimates of his ETAS, which is not easy to make errors. Posterior distribution, we can make a simulation based on the what do you think? What do you say the and stochastic? No. That's oh, let me think. Let me remember. The metropolis procedure around the maximum a posteriori estimate gives some using some simulation gives uncertainty.
Yeah.
It takes a very large calculation time.
Yeah, I know. Yeah.
So it depends on the model.
Okay. So, okay, it's finished. Okay, I think that the time is almost running out. I would have other questions, and probably I will send some email just to ask you some more details about. For instance, I'm very interested in understanding a little bit more something about the long-term background, including faults, for instance, how it could be included into ETAS. But for now, I think that the time is over, and I would like to thank you personally. It is always a huge pleasure to meet you, and I really do hope to meet you again soon in person. And thank you again, and for all the people here that I really appreciate your presentation and your paper as well. So thank you very much, Ogata-san, and see you soon.
Thank you very much for listening, and thank you very much for this chance. I appreciate very much.
Yeah.
Thank you very much.
Okay. Thank you to you, and I think that yeah, the seminar is over. Okay. Thank you again very much. Thank you.